Alright folks, sorry about that. I took the liberty off camera to basically type an array of numbers from 1 to 50, right, just to illustrate the method of receive of Eratosthenes. Anyhow, this was a Greek mathematician, famous for being for lack of a better word, the head of the Library of Alexandria for many years, which is a very noble distinction, I would think. Anyhow, this is a method of basically calculating or determining prime numbers. Here's an example. All right, it is to find all primes less than or equal to 50 in several steps. I'm going to pull up this thing that I just drew, so you don't have to physically draw it yourself. You can just use this and scroll slightly here. Okay, here's our array. And I believe it's off the board because I like to project onto that. So you can basically see it, right? Okay. The procedure works like this. You create your list, draw the array, whatever the parameters are, we're basically drawing from 1 to 50. Number 2, you cross out the number 1 because it is not a prime number by definition. We already know that the definition of a prime number is that it has 2 factors, and technically the number 1 has just 1 itself. Step 3. Circle number 2. And then basically step 4, cross out multiples of 2 by counting by 2, so multiples. It would technically be 2 times 2, which is 4, 2 times 3, which is 6, 2 times 4, which would be 8, all right, and so forth. But if you count by 2s, it's the same difference. So we're going to cross them out. 4 is a composite because it has 2, 1, and 4 as factors. 6 has 1 and 6, 2 and 3 as factors. It is a multiple of 2 as well. 8, 10, 12, 14, 16, 18, 20, this is kind of fun, right? 21, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, and 50 itself. One must be crossed out. And we're basically going to repeat the process. We already have our array, we already crossed out the things that we could, but we're going to step 5, repeat. All right. That is circle 3, and then 6, cross out multiples of 3. 3 is a prime, which is what we're after naturally. Now count by 3s, or if you know the multiplication tables of 3. Right. 6 would be the next one, it's already accounted for. So 3 times 3, 9 goes. 12 would be the next after that, but it's already accounted for. 15, 18, same situation. 21, remember 21, 1 times 21 and 3 times 7, so multiple of 3. It is a composite and a prime, goes away. 24 is already accounted for. 27, 29, no, it doesn't include that. 30 is accounted for. 33, 36, 39, 3 times 13. Let's see, 42 would be the next one. Pardon me, 45, 3 times 15. 47, no. 49, no. That's it for threes, I believe. Okay. And we're going to circle the next prime, which would be 5. And again, cross out multiples of 5. So let's see. 15 already squared away, 10 is already squared away, 20 as well, 25, 30, 35, 40 already done, 45 and 50 would be again. Next prime is 7. All right, cross out multiples of 7. All right. Let's see. 14 already done, 21 already done, 28. And 35 and 49. Basically, you will repeat this process until, put this over here. Officially, repeat this process until reach the prime number we'll call P, that when squared is P squared, it is greater than the limit. In this case, the limit is 50. 7 times 7 is not the prime number that we stop at. All right? We're going to check the next one, and then we'll say for sure. The next prime number would not logically be 11. 11 squared, all right, would exceed, would be greater than 50. So now we're officially going to stop. All right? And we'll circle the leftovers. Just to reiterate. We went with 7 because 7 times 7 is 49. That's not greater than 50. It's just shy of it, naturally. The next prime number, 11 squared, is 121, which definitely is beyond 50. Anyhow, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. If we were set to task, find all the prime numbers that are less than or equal to 50. In this case, it doesn't include 50, because 50 is just not a prime number. It is this set. It is 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. It's an interesting technique, right? Kind of fun, as long as you have the array already set up and don't have to draw it from scratch. All right. Next thing. let's discuss rules of divisibility. I made, again, there's a handout for you to print in Canvas. Let me pull this down again. This is a list that you can keep handy. Let's make it a little bit larger. For deciding what numbers are going to, again, divide nicely. Right? Most things can be divided, but not everything is divisible. 2 will divide nicely into any number. If the number is an even number, the dividend essentially. If the dividend is an even, then you can divide by 2 nicely, no remainders. A whole number for an answer. The sum of the digits 3. Let me just put a little asterisk for ones that are good to know. This is a little off the board, so I'm going to move the slide. And then just tell you which ones that are good, handy to know. That. And I'll discuss the complicated ones here. I don't know if you can see that, but if you print it, it's a little blurry. I basically stole this from the textbook, right? Here's the ones that I was conditioned to know by heart. The rule for 2, the rule for 5, and the rule for 10. Those are the ones I remember having to memorize, all right? I have found it since more practical to know 3 and 6. Right. And in this order, basically 2, then 3, then 6 first, then 5, then 10. We'll see what I mean in a minute. There are these rules for 4, and for 8, and for 9. Right? 9 is kind of similar to 3, and 4 and 8 are kind of similar to each other. But to me, Rule 4 and Rule 8 are maybe more trouble than they're worth. Right? Let's go through the list here. An example. If you had to determine whether this number, 963,888, is divisible by 2, 3, 4, 5, 6, 8, 9. You use their rules. Let me erase this. Let's say this is a multiple choice question. Is it divisible by 2? Now that boils down to, is this number 963,888 an even number? It most certainly is, because it ends in an even number, and automatically therefore is even. So you could definitely divide by 2, the remainder will technically be 0, or you could say no remainder, and therefore it's divisible by 2. So 2 checks out. B, is it divisible by 3? Here's where we start getting into a complicated rule. You can test to see if the number divides essentially nicely by the number 3 by following this rule, sum of the digits. If the sum of the digits produces a number that happens to divide nicely by 3, that is, there will be no remainder, it's divisible by 3, then the whole original thing would also be. You have to do the actual arithmetic in this case. You would be doing this. 9 plus 6 plus 3 plus 8 plus 8 plus 8. But 963,888. Added together, 6 and 3 is 15. 15 and 3 is 18. 18 and 8 is 26. 26 and 8 is 34. 34 plus 8 is 42. Does the number 42 divide by 3 nicely? That is to say, is 42 divisible by 3? Well, you could pull the same trick basically and add the digits and get 6, and I would say, yeah, 6 definitely works. Or you could brute force yourself here. 3 goes into 4 roughly once with 1 left over. 3 goes into 12 certainly 4 times, so yes. Alright. 3 works out. You could divide the number 963,888 by 3, and it will produce no remainder. Or will not produce remainder. It will be 0 technically. Okay. Probably would be smart, like something like numerology. Add 4 plus 2, keep crunching numbers basically until you get it down to a regular single digit. 6 would work nicely with 3 obviously. Okay. C. Divide by 6. This is the reason why I would suggest doing it in this order, alright? The rule for 6 is easy if you've already tested rule 2 and rule 3 successfully. The rule for 6 is if the number is divisible by 2 and 3, then the number is also divisible by 6, which when you're trying to simplify fractions, some forthcoming subject, that's a strategic way of going, all right, 6 is a better choice. Anyhow, we've already seen 2 works, 3 works, therefore 6 works. Then I would do 5. Right? Divisible by 5 is super easy. All right, the rule for 5 is, does it end in a 0 or 5? No, certainly not. So there's our first flub here. It doesn't work with 5. 10, because it's almost the same rule, would have to end in a 0. Still not ending in a 0, it ends in an 8, it's not going to work. 10 either. Right. Then these last rules, right, which I'll circle. These are the more complicated ones. Maybe try 9 first. Is the original number divisible by 9? The sum of the digits of this number is divisible by 9, then the original number, the whole kit and caboodle, would have to be as well. Well, the sum, as we've already checked, is 42, so no. Alright, it's not going to work with 9. Alright, you would really need to either have a calculator on hand or know your multiplication tables by heart, which is always ideal. 42 divided by 9 is 4 point something. Yeah, before this is 36. 9 times 4 is 36, is too short. 9 times 5 is 45, is too much. So it's not going to work with 9. Anyhow, doesn't work with 9. There we go. Let's see. A, B, C, D, E, F, G. Alright, is it divisible by 4? Let's see. The rule for 4 is the number formed by the last 2 digits. If the number formed by the last 2 digits, in this case, it's 88. That is divisible by 4, then the whole thing again, the whole kit and caboodle is also divisible by 4. So, well, can you divide by 4 nicely into 88? You most certainly can. Alright, just like you could divide 4 nicely into 8 by itself. 22. So yes, works with 4. Alright, and then there's 8. Alright, the number formed by the last 3 digits of the number is divisible by 8. That is to say, if 888 divides nicely by 8, and it does, then the whole thing is also divisible by 8 as well. And certainly 8 goes into itself multiple times nicely. 111 works. So, determine whether this number 963,888 is divisible by these choices. Right? It works with 2, 3, 6, and 4, and 8. And it doesn't work with 5 and 10. if you wrote it in fancy braces, and most of the times that's the case, they probably put it in set notation. That is to say, it works with 2, 3. Probably in numerical order would be ideal as well. 4, 6, and 8. Let's get into prime factorizations. And again, let's see. I'm not going to get to that yet. Let's discuss prime factorizations. I'm going to erase this. Try to get a blank screen here. It's a little bit easier to draw. Let's see. That's a little better. Okay. Prime factorizations I mentioned before. Basically, the product expansion of an actual number, right? So you'll see a bunch of numbers, exclusively primes, that are separated by multiplication in x's or dots. Now, there's two methods for deriving them, prime factorizations. Obtain, get prime factorization. It's not so lacking eloquence. Factorization. Okay. There's famously factor trees. I would bet is if you had gone to school in the United States locally. New Jersey, and probably elsewhere. This is the brainwashing that you were taught. All right, here, kids, draw this factor tree. Or there's this other method which is also useful, but I don't know how else to call it, but to describe it, it is this. It is upside down division by primes. That is exactly what it is. That isn't very particularly eloquent either. But that is what it is. All right. Now the textbook refers to this as branching, which is maybe more concise. And the textbook simply refers to this as division. But that's kind of vague, if you ask me. Anyhow, let's do an example. If you had to get the prime factorization of the number 220, you would, and we'll do it both ways. We'll do it factor trees first. You basically draw two branches, flanks, as you will, and try to conceive of a pair of numbers that you may know that multiply together, two factors that make this number. Right. There are some shortcuts in mental math skills that maybe if you went through grammar school, they taught you. This ends in a 0, right? We kind of just discussed divisibility So it would definitely be 10 times something. It turns out it would be 10 times 22. Alright. If you wanted to, you could always do this brute force. If you know that this ends in a 0, then therefore it is divisible by 10, therefore 10 is a factor. You could then punch this in. Right? 10 goes into 22 roughly twice, which is 20, and the difference is 2. And 10 goes into 20 exactly twice again, hence 22 here. Anyhow, you start in doing this with any pair of factors, legit pair, right? Except, one is a number times something. Don't use that because that isn't really making any headway. It's just repeating. If I put 1 times 222, we're still in the same place we started. Anyhow, you keep going, you keep breaking it down, keep factoring until the bottom rung of this tree is all primes. Again, it would be good to know the prime numbers 2, 3, 5, 7, 11, 13 at least by heart. Right? So you don't have to go through any methods, any sieves, that sort of thing. Just keep factoring. Right? You might ask yourself as you're going through this, well, is 10 a prime number? Certainly not. All right? It doesn't appear in our list of memorized primes, 2, 3, 5, 7, 11. So therefore, you could break this down. Break it down into ideally primes, if or something at least that works. Now it just so happens that this is a pretty finite list, right? 1 times 10 makes 10 and 2 times 5. Both of those are prime numbers, so we're good to go. 22, not prime, composite, so we can break this down. Again, knowing your multiplication table certainly helps in this case. What may come to mind immediately is 11 times something, and in this case it's 11 times 2. This technically is the prime factorization of the original quantity 222. What that means is that if you were to multiply all of these things, yes, it's a jumbled mess right now, you would get the original quantity. As a way of certifying, you know that you don't. Anyhow, there is one extra step. The extra step would be use exponents to abbreviate. That'll become more practical when we get into least common multiples and GCS and such. Anyhow, it would be good to put it in descending order. Let's start with 11. How many 11s are there? 1. So using an exponent, although it would be overkill, would be 11 to the first. Then it would be 5. We use dots at this point. 5 also to the first. This is only 1 5. And then how many 2s are there? Coincidentally, 2 2s. So this would be the ideal prime factorization. Something that is descending, and the use of exponents for the sake of conciseness and abbreviation. You know what the answer is? I'm going to do the same thing now using this other method. Upside down division by primes. It's a little bit more involved. Right? It does entail short division, which, although I didn't mention it to this point, you know that there's long division, which is usually what I do when I do a calculation on the board in front of you. Short division is basically writing sort of superscripts instead of writing a product underneath the dividend. Doing some of the calculation in your head, short division. Anyhow, this process, which I want to separate out from here, works like so. Right? You're going to start with the lowest prime that is divisible. Again, just to reiterate, what is divisibility? When something divides nicely. we say that that number divides, I'm double talking here, a number is divisible by another number if it divides nicely. No remainders. Alright, we're going to start with the lowest prime that is divisible. It is divides nicely. Again, lack of eloquence, but you get the point. We already know what the answer is for 220. But I'm going to do this. If it is truly division, then I have to draw the division box. But it's upside down, at least according to the orientation that I was taught living in the United States my whole life. Right? I have seen as a teacher, my students that come from the islands or from other parts of the world, they normally draw like this, the division style. The box sort of upside down. No sin in that, obviously. But where the quotient would go is going to be here rather than on the top. Okay? So anyhow, we have our rules of divisibility established. All right? A number is divisible by 2 if it is even. The number 220 ends in a 0. All right? Therefore, it is an even. Right? So you could definitely use 2. All right? And we're going to do again short division. I'm not going to stack anything up here. I'm just going to put little subscripts or superscripts if necessary. 2 goes into itself once. All right? Zeroes out. 2 goes into 2 again once. Zeroes out. Everything goes into 0 0 times. All right? You're going to basically continue with the same prime until you can't use it anymore. Exhausted. Right? Until not working anymore. So this is still an even number, therefore you could still use the number 2. 2 doesn't go into 1, it's too small, but 2 goes into 11 roughly 5 times. This is where short division comes in hand. The difference of 10, which is what 2 times 5 is, would be, subtract 11 here, would be 1. So I'm going to squeak in a little 1 here. Then read it as 2 into 10, right? Rather than carrying a 0 down. You see why it's upside down, at least from my perspective. 2 goes into 10, again, exactly 5 times in this case, and it zeroes out. Right? No remainder. We would continue with the number 2, all right, if it still worked. But it's not going to work because no longer an even number. All right, 55 is certainly an odd number. Ends in a 1, a 3, a 5, a 7, or a 9, it's an odd. If it ends in a 0, 2, 4, 6, or an 8, it's an even, by definition. And you might wonder, well, how do you know when to stop? Right? If you start with the lowest prime that is divisible, right, you basically, I'll put it here, you stop when the quotient is also prime. It's the whole point of the exercise is to get the prime factorization, which is to write the original quantity, namely 222 in this case, exclusively in terms of primes, then we would stop when we hit a prime as a quotient. Anyhow, next number after 2 that is a prime is 3. All right? The rule for 3, remember, is if the sum of the digits work, you can always brute force divide and see if it works, but spare yourself a little bit of trouble. If the sum of the digits, which in this case would be 5 plus 5 is 10, divides nicely by 3, and it doesn't, right? Then you could use 3, all right? You would end up with 11 in the third, right? So it's no dice. Not quite 11. Something terrible. 1, 2, 18 in the third, rather, right? Anyhow, the next prime number after 3 is 5. So does 5 work with something that ends in a 5? According to the rule, definitely does. So we use 5. 5 goes into itself exactly once, goes into itself again exactly once. And we know to stop because the quotient is also a prime number. This junk that is on the outside here, looks like a hot dog, right, is the same prime factorization we had established with factor trees. This takes a little bit of getting used to, but it is actually handy. Alright, so it's nice to have always sort of reserved in the back of your head. More than one way to do something is often the case. Alright, use abbreviations again. This is 11 to the first, this is 5 to the first, this is 2 squared. Right? This is more or less the ideal way to write it. GCFs. This is the last piece of paper in the pack. Right, 2 methods for calculating greatest common factor or greatest common divisor, which is what your textbook calls it, and least common multiple. Let me pull it up over here. This, you could always, if you have to, right, to get a GCF, make lists, but alternatively, you could use prime factorizations to calculate it, or to determine it, I should say. I need to rerun the diagram for reference, to make some distinctions here. First of all, for the sake of comparison, greatest common factor divisor, we're going to go and call it, versus least common multiple. And if you're curious what those abbreviations stand for, do that. That's being lazy. Now, first of all, involves, I'm boring myself, factors, and this involves multiples, and people often confuse these two things because they both involve multiplication somehow, but they're different, and I'll give you an example in a moment. For right now, the generalization about these factors make products. The things that you multiply together. Something times something. These things are factors. Multiples, on the other hand, are products. They're the result of multiplication. So for an example, you could list factors of 12. There's thankfully a finite amount of them. 1 times 12, 2 times 6, and 3 times 4. We have them in numerical order. That's all of these things. They would be in pairs naturally. So 1 times 12, 2 times 6, and 3 times 4 are all factors. They're things that make the product of 12. At the same time, you could actually list multiples of 12. And the difference right off the bat is that although factors are finite lists, multiples are infinite, which is why we want the least normally, because you'll never find the greatest if you try effort. 12 times 1, 12 times 2. Knowing the multiplication tables of 12, helps when you're doing this. I'm going to put the ellipses. 12, 24, 36, 48. It's no coincidence when I gave you that extra credit assignment from a while back, it was multiplication tables of 12. Anyhow, just know that they both involve multiplication, but one is the result, one of the parts, basically. These are the parts. These are the end results. Alright, now, what are they for? Alright, they have a purpose. GCFs are basically for the purpose of simplifying fractions. Least common multiple is for the purpose of doing exactly the opposite of that, but unfortunately there is no word in the English language or phrase even in the English language that really gets at that point. The polar opposite concept of simplifying. So I use this phrase myself. Upgrading. Upgrading fractions is usually with a common denominator. Simplifying is making things smaller somehow. Least common multiple is upping the ante. They're sort of upgrading, making things larger rather than smaller. So the opposite of simplifying, I can't think of any other word, upgrading, if you will. All right. Now, as for actually finding the greatest common factor or the least common multiple of two or more numbers, there's a brute force way of doing it, and then there's this prime factorization method. So let's just make sure we're clear on that. How to get GCF. How to get LCM. GCF, you could list and compare, which is more or less what I had been doing right there. I only did it for one number, 12. I listed factors of 12.
Or you could use prime factorization.
I'm sorry. Okay. Similarly, if you're finding an LCM, you can list multiples and then compare. That's even more cumbersome though because of the infinite nature of the lists. Maybe quite a while before you actually stumble across the answer. So you can then use prime factorizations, and this is sort of the preferred way of doing it by hand. Okay. Now let me show you what this describes here. The method that is not listing with using prime factorization. Both cases are very, very similar. Okay, I'll use the numbers 25 and 35 in both cases. Right. You can get the prime factorizations of the number 25 and 35 independent of each other. And then use abbreviations using exponents. And then purposely select the lowest power of each base that they share in common. That's the one distinction here between looking for this GCF and looking for this LCM. You'll see we'll do it twice. I'm going to use trees just because it's easier. And then I'll do it the other way, because you'll already have seen it done with trees. Here's 25. What comes to mind when you think of two things that multiply together that make 25? Well, if it isn't 1 times 25, which you shouldn't use anyway, because 1 is not a prime, then it would be the only other choice, which is 5 times 5, right? That right there is the prime factorization, because you've struck the prime gold here, just primes exclusively. Use an abbreviation though. It would be 5 squared. Right? At the same time, if you did 35, and you try to conceive of two numbers again, multiplying together two factors that make 35.
It would be 1 times 35, but again, you don't use 1, and it wouldn't make any progress anyway.
And in this case, you'd have to go with 7 times 5, so you wouldn't have to delve too deeply in order to get to the answer. Anyhow, this is the prime factorization of 35. Right? And using abbreviations, exponents, this would be 7 to the first and 5 to the first. Okay. Now, we're going to select the lowest power of each base in common. They don't have the number 7, the base number 7 in common. We're only interested for GCFs anyhow in the things that they have in common. So our eyeballs are basically going to be looking exclusively at the 5s. We want the lowest power that we have to choose from. This is the reason why I use exponents for abbreviation. This is 5 squared, this is 5 to the first. The lower power would be that one, not this one. So, what's our GCF? It's just 5 to the first, which is really just the number 5. Now granted, if you did it the slightly more brute force way, which is to list factors of 25 and factors of 35, it wouldn't take too long in this particular case. It would be 1 times 25 and 5 times 5, which you only write once, and 1 times 35 and 5 times 7, and you'd see that's the greatest common factor, right? Everything has 1 as a factor, but we want the biggest thing, the greatest thing, and in this case it would be 5. Anyhow, I would still hang on to this method because it's useful, right? Again, not to confuse you, but when you're looking for LCMs, you really would prefer to probably do it this way. Get the prime factorization however you do, upside down division by primes or trees, whichever you like. And then modify the technique slightly. This is the train of thought here. We already know what the prime factorizations are. Just for the sake of practice, I'll do it upside down division of prime style. You don't have to, but here, here's 25, and here's 35. When you perform this sort of upside down division by primes to get the prime factorization, right, you start with the lowest prime, which is 2, if it works, right, and if it doesn't work, move on to the next lowest prime. 2 doesn't work in either of these cases because they're not even. This is an odd number, that's an odd number, right? Next prime number is 3, sum of the digits. 2 plus 5 would be 7. 7 does not divide nicely by the number 3. It's not divisible by 3. So we would move on to the next, which is 5. 5 would definitely work with 25, and the outcome, coincidentally, is 5. That's your prime factorization, which again is 5 squared. We've already eliminated 2 here, so it's not even. Sum of the digits. Sum of the digits of 35 is 3 plus 5 is 8. 8 does not divide nicely by 3. It is not divisible by 3, would be the more eloquent way of saying that. So we move on to the next prime, which is 5, if you already know. 5 certainly works with this, and it's 7. That's a prime number, we stop. And this is 7 to the first and 5 to the first. Right. Now here's where these things deviate from one another, diverge. When you're looking for the GCF, you want the lowest power. That's the first thing. When you're looking for an LCM, ironically, you're looking for the highest power. But it's even more complicated than that. GCF is lowest power of the things in common, meaning they have to share something in common. In this case, you're looking for each unique base. Can't stress that enough. They have to be unique. You don't care if they share something in common or not. You want an example of each unique type of base of an exponent. So we have the 5s, which do coincidentally happen to be in common. Who cares if they are or not in this case? But we want the highest power, which in this case is this one. So I'm definitely going to use that as part of my LCM. And then not use this. Is lower. And then I'm going to also include 7, because again, it's unique things, not things in common. So 7 to the first, right? And then straighten it out. 5 squared is actually 25. 7 to the first is really just 7. 7 times 25, think of quarters in a dollar. There's 4 quarters in a dollar, and there's 8 quarters in $2, so just shy of 2 would be 75. 175. If you had to list multiples in this case, you see that it's kind of impractical. First of all, if you did 25, it's not too bad. Because counted by 25s is somewhat familiar if you ever played around with money. 25 cents, 50 cents, 75 cents, and so forth. But you would not know where to stop intermittently. So you might go a little far, and you go, oh geez, I don't know where to go. and try 35. And 35 is a less warm, fuzzy, and familiar number. So although you can figure it out, 35 times 1 is 35, when you get to 35 times 2, you probably don't have that memorized. All right, it would be 70. And you say, well, it's close to 75, but close but no cigar. And then go, what's the next one? You would add possibly 35 to that, get 105. And go, no, so now it's overshooting it. First it was too short, and now it's overshooting it. And you go, all right, what's the next one? 105 plus 35 is 140. And now you're well past 100, and you have to go back to this list and go, all right, the next one is about 25. Nope. The next one is about 50. Nope. And then you go, well, all right, I'm past 140. And you go back and forth and toggle, and it's kind of annoying. Anyhow, eventually the next one would be the match in both of these lists. So rather than go through that exercise of comparing back and forth and not really knowing for sure where to stop, keep this method in mind, right? When you use trees, we use upside down division by primes. It's this train of thought, right? It's slightly distinct from this train of thought for finding GCFs and LCMs respectively. Now, that was section 5.1. We do 5.2, because I absolutely must. Make up for lost time. Thankfully, since we're not, I didn't think I would say this, but since we're not here, I am. I'm having a hallucination of a class right now. Since you guys are not here, thank you. You could watch this whenever you want. I'm sorry it's kind of running long. I'm going to have to edit together these two videos. But we can get through the material that we're behind now. Let me explain this diagram. There is actually another page in that packet that I was talking about, and which you can print. And I think I may have drawn it for you before because it came up in conversation, but I actually took the time to draw it in PowerPoint, so I'll just flash it here. I'll talk about it a little bit more. Okay, here's your this family tree. This is section 5.2 now, which is officially number theory of the integers. Okay. It's good to have some organization in your mind about numbers, right? I like to call this a family tree. Right, the first sort of dichotomy here, and I hate the term imaginary, but it gets used, right? Usually the instructions when you're reading them either as an adult to a child or when you were a kid yourself, right? I always thought it was kind of confusing to say, find all real numbers. What does that mean? I'm just using the same numbers that anybody else is using. Are they all real, or at least abstractly real somehow? It's kind of an oxymoron. Well, no, there is this other category technically. You're not responsible for this, but just to make this distinction, why use the word real? Because this is other category. An imaginary number is the square root of a negative, all right? It doesn't have to be -1 per se, but that's the most basic example. The problem with a square root of a negative is that there is no answer to the question, right? What are the identical factors that make -1? Well, if it was 4, which is really +4, it would be +2 times +2, that makes +4. Those are the identical factors that make this number. That's what a square root asks. Alternatively, -2 times -2 also coincidentally makes +4. So it means there will be 2 answers in theory for a square root. When it comes to something that is negative itself, though, although I can conceive of the question, there is no answer because there are no identical factors, right? The digits are 1 here and here, but the sign combinations would have to be one of each sign. A positive one and a negative one produces a negative one as an outcome. So, because I can't answer the question, we say that this is an imaginary number. All right? Beyond recognizing that, you don't have to worry about it. What's more important are these other categories and subcategories here. A real number, the first dichotomy after that is whether something is rational or irrational. In a nutshell, anything, whether it looks like it or not, that is rational can be a fraction. For example, 3, even though it's a whole number, can be disguised essentially to look like a fraction. How so? Stick a 1 under it. Right? Even the fraction of, the decimal point 3 is 3/10. It's sitting in the tenths place, right? So its denominator is 10, right? Even a repeater, like 3 with a bar over it, which means 0.333 forever and ever and ever, right? That comes from 3/9, which simplified is 1/3, comes from a fraction, right? There is actually a method that we'll get to in the future of finding the fraction, not just simply memorizing it. But for right now, just realize whether something is a whole number, a terminating decimal, or a repeater, they all can be written in the style of a fraction. If we would extrapolate, right, if rational I'm saying is something that can be a fraction, one would assume, and it's true, that an irrational can't be a fraction. Now famously, if you wanted to get down to the nitty-gritty and describe what's going on, this is what's going on. Irrational numbers are decimals that are non-terminating, which means they're going to infinity. And they have no perceptible obvious pattern, so that we say that they're non-repeating. Simultaneously, they are these two conditions. Famously, pi is 3.14159, whatever it is, right? Usually you get a kid to memorize the first 3 digits and call it a day. Say, oh, it's 3.14. And that's fine, because when you're doing practical math like geometry, you can't multiply for the rest of your life. You have to go to bed at some point. Anyhow, it actually stretches well beyond that, and it has, as you can see, no real pattern to it. Then there's other numbers like E, Euler's number, or which is what, 2.71 something into infinity. Square root 2, 1.41 something into infinity. Right? There's a whole slew of famous math numbers. The superstars, I've heard another person on YouTube actually say that. I like that expression. The superstars of math. Anyhow, the integers, as you know from before, are basically whole numbers. But they could be negative, they could be positive, or they could be the in-betweener, 0. But they have the wholes. Right? And there's decimals. Decimals can be terminating, as in the example of 0.3, or repeating, as in the case of point with a little hat in wallet notation, to indicate that that digit repeats. It could be an example of just one number that shows up more than once, or several. If you have the bar extended over 1 and 8, then it would be 1, 8, 1, 8, 1, 8, 1, 8 forever and ever. Anyhow, since we're in the subject of integers, they start usually at this point in the subject of math, drawing pictures. Draw a picture to summarize, right? Especially the integers. 0 being in the middle. On one side of this number line is an arrow indicating this stretches further this way into negative infinity. And the arrow on this side stretches into positive infinity. Looks like a sideways sloppily drawn in this case. And they're incremented. 1, 2, 3, 4, so forth. And then there's this mirror image. We have negatives. Notice they're getting further away from 0 in this direction. They're negatives. They're more negative this way. Let's discuss comparison symbols. there are symbols for comparison, which famously are these, right? Less than, or oriented this way would be greater than. And then technically this bunch is obviously equal, is not equal, which is kind of vague. And then there's squiggle equals, which is about equal. These are not going to come up too often aside from any equals. Everybody just takes that for granted anyway. These two, the inequalities, they get used a lot. There's also another set, less or equal. And this greater or equal. I think primarily for now it's these two that you have to worry about. Now, if you're comparing integers, all right, it can get a little tricky. So let's establish some rules here. And some basic ground rules. You don't have to draw a number line. I think a lot of textbooks encourage kids to do that, and they tell them, "Now leave this way, do it that way." And there's really no sin in that, but to me, if you had to do that every single time, all right, it's probably more trouble than it's worth. So these two rules will get you pretty far, all right? A positive is always greater than a negative, always, regardless of the magnitude, that is the size of the digit. A negative closer to 0 on the number line. Is always greater than a negative farther from 0 on the number line. Here's some examples to refresh your memory. Let's do these four. Give you some hints here. Let's compare 3 to 5. And then -3, -3 to -5. And then let's do -2.8, it's a decimal, compared to -2.7. And then I'll do one other one here. -4/7 compared to -3/5. There's a trick to that. Now, just using these two rules, positives are always greater than negatives, no matter what size the digit is. The negative that is closer to 0 on a number line is 0, is your negative, is going to be greater always than one that is much further from 0. Closer, farther, I should say. Further is where English gets me in trouble. A description of depth. You know? Farther is horizontal distance. Anyhow, what are the signs associated with these things? If it's not written, what do you assume they are? We'll go positive. So the normal rules would apply. All right? 3 is what compared to 5? Automatic. Less than. No question about it. It's a smaller number. But if the situation were assigned negative symbols for both of them, what's the relationship now? Positives are always greater than negatives. Neither of them is positive in this case. But a negative that is closer to 0 is greater than a negative that is farther from 0. In that case, this is the relationship -3 is actually greater than -5, right? Because it's closer to 0. It's closer to the positives, you might say. When you get a decimal, you basically need to compare the same place values. Places. All right, now for example, if you notice, these are both negative, so we're going to be focusing on this, rule number 2 here. And then you notice that in the ones place, they're both 2. Right, so I'm not going to make any fair comparison there, they're the same. No distinction, I should say. No contrast. But if you look at this 8 and you look at this 7, and bear in mind they're still negative. All right. They're both in the tens place, so they're an appropriate thing. We want to compare the same places. They're both the tens. Which one is technically closer to 0? The smaller looking one. So therefore, pardon me. Yes, this is the relationship. -2.8, in spite of its magnitude, is a negative that is further away from 0 than 2.7. -2.7, in spite of its magnitude, it looks small, it's like 27 versus 28, is closer to 0, therefore it is technically greater. When you're doing fractions, there's a shortcut. You could convert them to decimals, which is a whole ball of wax. The easiest thing is basically cross multiply and compare. This is a shortcut. Now let's multiply like this. 7 times 3 is what? 21. That's the digit. 4 times 5 is 20. That's the digit. Now, remember, this is negative, and this is really representative of a negative. So we're really comparing these two things. -20 compared to -21. And we're associating -20, this diagonal this way, with 4 sevens. And we're associating this -21, this diagonal, with 3/5. So, again, they're both negatives. So we're going to look at this rule again. Which one is closer to 0? 20. Therefore, that is the greater one. I get a 20 in spite of the magnitude of the number, which is 20. That's the size of the digits, basically. Is closer to 0, therefore it's closer to the positives, therefore it's greater. Here's some alternative ways of writing. If you have signs, positive or negative signs, and I want to stress they are between numbers. For example, if you had a situation where you have a double negative between numbers, between digits, you would see something essentially like this. A number here, whatever it is, a minus sign, and then another thing, and then another digit here. They sometimes will put a parentheses around this, and sometimes they won't bother. Anyhow, when you have a double negative, that means plus. You could rewrite the problem so that you just use one symbol. When you have this situation, sometimes we need, this is an alternative, let's just call it a single minus or a single negative, whichever you like, between numbers, something like this, some number minus some other number. If it behooves you to, you could write this split, big positive, little negative, like that. Same number here, same number here. Sometimes it's more conducive to do a problem in that way. So I'm just mentioning it as an alternative way of doing something. I'm sorry, somebody pulled me. people, even if they're on with a calculator, will get an answer wrong, I've noticed, because they're just not familiar with certain rules that they really need to memorize. Beyond even this. To summarize. And I should just, while I'm taking a break for a moment, I'm going to check the battery on my camera here, see if it's still functioning. Hopefully it is. Rock and roll, good. Let's discuss integer operations. Integer operations. Remember, operations are things that you do two numbers or do with numbers if you like. Adding, subtracting, multiplying, dividing. Right? There are conflicting sets of rules. So let's establish clarity here. There are the addition and subtraction set of rules. Right? And they are distinct from the multiplication and division set of rules. Okay. If you have, there's two. If you have same signs, you add. Whereas if you have one of each sign, you actually subtract. You may need to reauthor the problem, tweak it, to use, combine two double negative into a positive, or in some cases, maybe more rarely, you can take a single negative symbol and make it plus a negative, for the sake of deciding whether you have this scenario or this scenario. Right? Basically, the sign combos decide the operation. And in these cases, both these cases, the sign of the answer matches the larger magnitude. Magnitude is the larger digit essentially, but for technical reasons I have to use the word magnitude. Multiplication, on the other hand, has similar looking rules, but the combinations don't affect the operation. Sign combos do not decide operation. For the most part, if something starts as a multiplication problem, it ends as a multiplication problem. Right? Starts as a division problem and ends as a division problem. The only exception to that would be for a totally different reason, fractions. When you divide by a fraction, you multiply by its reciprocal, but that's something that's further down the pike. And that's a technicality, it's not for this reason. Anyhow, the sign combos determine the sign of the answer. So here. Okay, one. If you have same signs, means you have a positive answer. Whether it's a negative times a negative or a positive times a positive. Still gonna get a positive answer. Two. One of each. And a negative answer. Here's several examples to have for comparison. Okay, so I'm sure we duplicated this correctly. Same signs add, one of each subtract. Same signs positive, one of each negative. Okay. If you had this situation, you have -5 plus, and sometimes the textbook will write the integer in a parentheses to kind of isolate it, draw your attention to it. Start with this question, all right? It could be adding, it could be subtracting because of there's no multiplication x in it, and there's certainly no dot, division symbol. So it's either one of these situations, really. Are they the same signs, or are they one of each? Look at the isolated 3, look at the 5. This is same signs. So that means you're really going to add. And you're going to get a negative plus a negative is a bigger negative when you add them. You get -8 as an answer. If on the other hand, you had this, 15 minus 20. This is a subtraction problem, at least superficially, we'll verify. But we may have to dress it up a little bit to make it more obvious what's going on here. There's 2 ways you can go about that. I would just do it this way. What is the, what is the sign that's not written here? You would assume it is a positive if it's not written. So now just read it like this. Rather than go through this route, there's no harm in doing this if you want. It's just changing something from a subtraction looking problem to an addition looking problem, but it's really the combinations that will decide whether you really do one or the other. Anyhow, so just say to yourself in this form, one of each, both the same. One of each. If they're one of each, that means you're going to subtract them. That's going to establish the digit at least. 20 minus 15 is what number? 5. All right. It'll match this, the answer will match the sign of the larger magnitude number, the bigger digit technically. If you associate this sign with 15 and this sign with 20, then it's going to be a -5, because it will match the bigger digit. There's another one. You had 40 minus -8, and again, sometimes textbooks like to throw a parentheses in there. This is an example of alternatives. When you see a double negative between numbers, you can just consolidate them as positive. It really is technically multiplication, but I don't want to go there. All right. This is really 40 plus 8. This is 48, of course. And you could put positive 40 if it's an alternative. I need this space, so I'm going to put this here. And if you did this one, this is kind of your worst case scenario. -4 minus -3, lots of negative signs. And superficially, everyone would say, oh yeah, it's definitely a subtraction problem. Remember, it's the combinations that ultimately will decide that. You have here to start with a double negative, which alternatively can be just simply consolidated into this one single solitary plus sign. This -4 is here already. At this point, I would say one of each or same signs. So one of each. So you're really going to subtract these. In which case, you get the digit of 1. It shrinks because of subtraction. And it matches the sign. Now, the answer's sign will match the bigger magnitude number, which in this case happens to be negative. You associate signs like so. So, -1. Okay, here's the multiplication problem. 2 times -3. Again, if the information is missing, fill in the missing information. If 2 doesn't have a sign, assume it is positive, right? It's definitely a multiplication problem because of the x signifying that. One of each simply means that the outcome is going to be negative, but the multiplication is still ongoing, so 6 is the answer, -6. Right? Sometimes, as you know, they don't use multiplication answers, they use dots instead. So if you saw something like this, -7 dot -8, a dot in between, or even if they were just pressed against each other, one parentheses or two, no symbol in between at all. It's a multiplication problem, in which case they have the same signs, so you can certify that this is going to be a positive answer, and then 7 times 8 is still being multiplied to 56. Division problems follow the same sets of rules as multiplication. Just beware what is a division problem when you see it. Sometimes it's not so obvious. Like for example, you have this -63 sitting on top of 9. It's an improper fraction, right? But it is in theory a division problem. If you bother to do the minutiae, if you go through the fine details. Since it's division, which I recognize by that fraction bar, it's one of these alternatives, and that means divide. We're going to follow the multiplication / division set of rules. They are one of each. How come? If it was 9, you would have to assume it's a positive. So the only thing that these combos are going to decide is that it's going to be a negative outcome. It's still division. 63 divided by 9 is 7. Exponents. Or exponents, which is a glorified form of multiplication. Right. If you think about the timeline of your life, your math life, when you first came to school, they probably had the assumption, correctly or not, that you came to school knowing your alphabet and you knew how to count, basically. And then they said, hey, listen, you don't have to use your fingers. There are symbols that we have. So, and from counting, that the operations were based. And the first operation to replace simple counting is to do it symbolically with Arabic numbers, addition. They teach you the concept, and then they teach you the opposite of that, which is subtraction. A little bit further down the pike in the conversation of math, they teach you a slightly more sophisticated form of adding. Just like adding is a more sophisticated form of counting, well, multiplying is a more sophisticated form of adding. They teach you the concept, and they teach you the opposite of it, division. Right? And eventually, like in the United States, I could vouch for this. Usually like 5th grade, something like that, maybe 6th grade, sometimes 4th, I suppose. They'll teach you a amped up version of multiplication, which is what this is. Exponents, famously like squaring, cubing, etc. They teach you that, and its opposite, which is roots, and square root, effectively cube root, and such. A glorified form of division, if you will. Anyhow. The instruction again gets a little confusing. Here's an example, firstly, of something that involves exponents. Know the names of the pieces, it will help. The actual exponent is the number 3. This number is referred to as the base. And the whole thing is referred to as a power of whatever the base is. I can't stress that enough. So therefore, if it's a power dependent upon this number here, this is a power of 2, not 3. People say it wrong all the time, right? What can you say? Legally, not that people who aren't more important than me say it wrong by accident, and everybody knows what they mean anyway. The correct thing that you could say is not 2 to the power of 3. That implies that the base is 3, but it isn't. It's 2 to the 3rd power, right? Not 2 to the power of 3. Hopefully this is not getting cut off, right? English, when you're teaching math, sucks, right, for this reason. But just switching some of the words around here, and also noticing that the word to, T-O, is pronounced the same as the Arabic numeral T-W-O. It gets confusing. You want to read it this way, especially the kids, right? Because, again, it's a power of whatever the base is. So this thing is a power of 2, not 3. Right? 3rd power is fine. 2nd power is fine. 4th power, TH suffixes are fine. Right? They're correct. Then there's the instruction. Like when you first explain this to a kid, as you guys will inevitably do, you try to get it as clear and to the point right off the bat, but unfortunately, because English complicates things, it can get you in trouble, so do be careful. Here's what I mean. The actual instruction is this. Again, bear in mind, it's a glorified form of multiplication. The instruction is write, for this problem, 2 3 times, and then multiply. That's the most literal way of explaining it to a kid. There is a perhaps better choice of words, but remember, you're talking to kids who are maybe 10, 11, or 12, all right? So although I would broach the subject, I would introduce them to the word. The word is iterations, all right? Write 3 iterations in lieu of the word times, because it's, what's the word? The word times is ambiguous. Its context, you know, is dependent upon the things sitting around it, all right? You could use this as an alternative. You could say write 2 3 iterations, then multiply. But what does it mean literally? It means write the number 2 thrice, 3 times, right? 3 iterations, 3 clones, if you will, of the number that is the base number. And then multiply. Don't break your jaw. That's always a bad idea. Anyhow, what's 2 times 2 times 2? Well, it's 8, right? Now, here's an example again, where English unfortunately sucks when you're teaching math. The instruction is not this. Can't stress that enough. Write 2 times 3, and then multiply. Seems innocent enough. Right? Just switching the word times and the word 3 changes the context of the instruction. Right? Writing 2 times 3 literally would be doing this, right, in vernacular English. Anyhow, 2 times 3 is not 8, it is what? 6. Right? And 6 is not 8, therefore it definitely matters, right? This is the instruction. Write 3 times, pardon me, write 2 3 times, that's iterations, clones, if you will, of the base, and then multiply. Here's the absolute last thing. Well, order of operations. Another set of instructions, but it's a set of instructions that everybody must agree to. Because even if the person adds, subtracts, multiplies, and divides with the best of them, without a calculator, completely by hand or in the head, you know, a blessed person. If they don't do it in a specific order that we will agree to, they may or may not get to a different answer than what everyone else does. So this is the order of operations. This is what we will agree to. For math's sake. For math's sake, let him smoke. It's a line in the movie. There's a movie called Cold Turkey, and not to diverge from the subject here, but in the movie, the whole town gives up smoking, and so they're all stressed out. This took place in 1970. Anyhow, so there was a guy on an operating table who was about to have surgery performed by his doctor, and the doctor was shaking because he had a chemical dependence and it was not being satiated. Anyhow, the patient rises up from the table and goes, "For God's sake, let him smoke!" And they didn't. Anyhow, the order of operations is what we all must agree to for math's sake. All right. It's either PEMDAS, which I think more people are probably familiar with, the acronym. If it helps remember that you do the parentheses, the squaring, multiplication and division, and addition and subtraction in a particular order. Or there is a mnemonic device similar to an acronym, which uses words. Please excuse my dear Aunt Sally. I kind of prefer this, and that was because my beloved Mrs. Cavilio, Miss Cavilio, my third and fourth grade teacher, is probably the person who taught me this. She was great. She really was. Best. But this is sort of on tiers, steps. So it makes it a little bit more obvious that these two things that share the same step are equally important because they're on an equal level. Same thing with addition and subtraction. This is parentheses, those things must get done first. Exponents are things raised to 2, 3, or what have you. Those must get done secondly. And then multiplication and division, right, those get done third. But when you're trying to decide between them, there's a problem may include both of them. It's whichever is left, on the far left, or furthest left, I should say it that way. Farthest left. Same thing for addition and subtraction. When confronted with the choice between the two of them, you do whichever is farthest left. That's not what's left over. Again, English get you in trouble. Do those dead last. Let me give you a couple of examples, and then that's it. We're done with 5.1 and 5.2. Hopefully, YouTube will upload this. Otherwise, I wasted 3 hours of my life. It's never a waste if it clarifies things. I'm kidding, really. What would I do with my life if I didn't teach? I'd be a very sad person. Can't imagine myself in any other job, to be honest. Maybe something quiet, an art project, an archivist. But I think that this is a little bit more practical and better for my own cognitive ability. When you do basic math, even on a regular basis, it keeps you sort of sharp, mentally acute. Here's an example. You'll see instructions like evaluate, which means follow the order of operations. at this, 100 minus 3 times 5 squared plus 5. Couple of things. If anyone has ever said to you, hey, what's the answer? Do it quick. And if you don't, shame on you. Etch a sketch. Forget that thought. That is a lousy piece of advice. Don't do things in your head. If you want to, especially if you want to make them clear to another person, because no one can see in your head unless they have X-ray vision, and I don't know anyone who does. If you want to get through a problem like this, multi-operational problem, and you're doing it yourself, not with a machine, which you should be able to, right? Follow the order of operations, write an algorithm. Write it with little changes, step by step, line by line, until you take something long, complicated, and ugly, and you narrow it down to something that is concise and simple. Basically, this is more or less the pattern, right? Write an algorithm, line by line, all right? Let's look at the choices we have. Subtraction, multiplication, glorified multiplication, and exponents. Adding, all right? Technically, if you look at the PEMDAS, or if you look at, please excuse my dear anxiety, the order of operations, which is technically the most important thing. I would argue glorified multiplication, or complex form of multiplication, exponents. So your focus should really be here and nowhere else. I would just simply duplicate the stuff that is around it when I'm writing my algorithm, my step-by-step process. 5 squared is to write 2 clones of 5 and then multiply. 2 iterations. 5 written twice and multiplied. 5 times 5 is 25, right? Write it with that one alteration. All right? It's still the same length right now, but we're getting narrower. Right? Now you still have leftover subtraction, multiplication, addition, which is technically the most important now. The multiplying. All right? So just look at the digits for right now. Pardon me. 3 times 25 is 75. So 100 here, there's minus here, there's a positive here. And now at last, we're starting to get somewhere more concise. Notice that you have, again, the choice between adding and subtracting. They're on the same level. They're equally important. They're opposite concepts, but they're of equal importance. In the mnemonic here, shorthand comes up before Sally. It's like A comes up before S in PEMDAS, but that does not mean that addition goes first. It's whichever is on the left or far left, which in this case means your focus is now here. 100 minus 75 is 25. 25 plus leftover 8 is simply what? 33. That's what it is. Sorry. Here. One more, slightly more complicated, is this. Same instructions, evaluate, which means follow the order of operations, this set of procedures. If you had 41 plus 23 divided by 8 times 13 minus 15 squared. I have a lot of choices to choose from, a lot of alternatives to choose from. Right? You have some contents of the first set of parentheses here, and it's adding on the inside. Outside is division and multiplication, and then the second parentheses, contents of which are subtraction, and then there's an exponent on the outside. If you had to choose between which to focus on first, it's the P includes parentheses, all right? And similar to deciding between multiplying and dividing, it's whichever is on the left that you would do first technically. So if we're gonna narrow it down like this essentially, narrow your focus to here first, right? And then rewrite whatever this outcome is and then the jump that follows it. 41 plus 23 is just a straightforward addition problem. So it's 64. If you want, you can leave the parentheses, no harm done. Division 8 times, since I'm just trying to save void space is the only reason. If I want to, I can now know that I have to do the other parentheses. 13 minus 15 is a subtraction looking problem. The combination of signs would be one of each technically, so I am going to legitimately subtract, I'm just verifying. And you're going to get the number 2. So the sign of it though will be negative to match the larger magnitude number, which in this case happens to be 15. Still squaring. Now we have this 64, there's nothing in it, right? And if you want to, you could simply rewrite the problem without that. When I would get over here though, I'd be a little bit more careful because you have a sign to worry about. If you had to choose between division, regular ordinary multiplication, and squaring, which is amped up, super turbocharged multiplication, I would leave this in the parentheses because if the exponent is on the outside, it's signifying that both of these things is being affected by the exponent of 2. You're in other words going to duplicate the number -2. Clones 2 of them. -2 times -2. A negative times a negative is a positive. So that's the number. You could put +4 if you want. We'll leave it alone. All right. You could put this in a parentheses and do that, but it'd be kind of overkill, I think. Whatever you feel more comfortable with ultimately is fine, especially if you're unfamiliar with this. But a conciser way of writing it is just to simply write the digit 4 rather than +4, which it is. Now you have the choice between division and multiplication. Again, where should your focus be? Well, shifted from here to here, and now it is here again, because multiplying and dividing are equally important. They're on the same step. They're on the same tier. They both get the bronze, if you will. Gold, silver, bronze, copper. Stupid analogy, whatever. 64 divided by 8 is just 8. So you have 8 times 4, and there's nothing else to combine. You get a similar number, 32. Okay. If it comes up in conversation, and it is more theoretical than maybe practical, there are names subscribed to things that you might take for granted. If they speak of properties in math world are basically very formal ways of saying that something is what it is. Like for example, 0 times anything is 0. There's a 0 property of multiplication. Basically is formally written as something like this. A times 0 is 0. A is in anything times 0 equals is 0. And there's this, the additive inverse property. Is this. A number plus its opposite sign is equal to 0. These are very similar because they both involve 0 somehow, but one involves adding or subtracting potentially, and the other multiplication. This essentially is saying that anything times 0 is 0. This is saying that a number plus its opposite same magnitude but opposite sign will produce 0. This is not a formal property, but do remember, division is not commutative, which basically means the order in which the problem is written matters a lot. example, anything, well, let's just say a number n divided by 0 is not the same thing as 0 divided by a number. This is dividing by 0 on this side here. This is by 0. This is into 0, essentially. The outcome of this is that it is undefined. The outcome of this is 0 as an answer. 0 does not mean undefined. They're distinct. All right. The reason is because it's not commutative. Division is not a commutative property. Multiplication is, addition is. Right? If you tested out these figures here, if this is the answer, these two things, the quotient and the divisor multiplied, should produce the top here. A number times 0, according to the zero property multiplication, is definitely this. All right? However, let's say that a person thought these were the same things. The quotient and the divisor, if they were multiplied, do they produce a number that's not 0? 0 times 0 would be 0. But this could have been something else. It could have been 5, could have been 100, could have been negative 22. All right? It's undefined. All right? This is not legitimate. Okay. So, as for homework, we're basically inching closer to where we should be. This is section 5.1 and 5.2 that got covered today in this bunch of video segments, which I'm going to try to join together, but we'll see if YouTube will let me do that. Where should you guys be at? You know, my calendar, and I'll say certain, and I'll write it here for reference. For homework, in my lab, right, do the prerequisite, right, do section 5.1, and do section 5.2. Right, there is nothing else pending. When we come back on Monday, I'm going to try to squeeze in all of section 5.3. Just to point at my calendar again. It has to be adjusted, of course, but I'll pull this back in a minute. We did 5.1 and 5.2 here today on the 18th. Well, it's for the 18th. It's actually St. Patty's Day today. But you'll hopefully see this tomorrow. 5.3, both parts, I'm going to do Monday of next week, by hook or by crook. And the review day, I'm just going to forego and do section 5.6. Right? And then, as far as tests are concerned, I still got to work that out. We are assumed to be not in school still until maybe April. Right? At least that's the last thing that I heard. Maybe they'll rescind that. But anyhow, I can't give you a test on Proctor, really, right? So I think I may just end up giving you my lab assignments for the foreseeable future. I'll tell you for sure when I finally, you know, I have to make a decision, but right now it's up in the air. All right, anyhow, make sure you do 5.1 and 5.2 in my lab. And there's always a prerequisite section, so please try that too. All right. Thank you for your patience. All right. Again, I'd give you the papers if I could, but I can't. My hallucinated class here, thank you for coming. All right, and hopefully everything will upload nicely so you can watch this whenever you really have time, all right, between now and Monday. All right, thank you, guys.